In the previous module, we have introduced the continuous time Fourier transform. Let us code the equations once again. The continuous time Fourier transform equations are as follows. It says that if you have a continuous time signal x of t, its continuous time Fourier transform is given by x of omega, that is equals to integration from minus infinite to infinite x of t e power minus j omega t dt. We can reconstruct back the original signal x of t by using the synthesis equation that is given by 1 upon 2 pi integration from minus infinite to infinite x of omega e power j omega t d omega. Now that we are aware of the continuous time Fourier transform equations, let us look at the properties of this continuous time Fourier transform. The first property that we are going to look at is the most common property, that is the property of linearity. Linearity property says that if we have a linear combination of signals, say for example a times x1 of t plus b times x2 of t, then its Fourier transform is given by a times x1 of omega plus b times x2 of omega, where this x1 of omega and x2 of omega are the individual transforms of x1 of t and x2 of t respectively. What I mean to say here is that if we have x1 of t whose Fourier transform is x1 of omega, if we have x2 of t as another signal whose Fourier transform is x2 of omega, then a linear combination of x1 of t and x2 of t with the combination constants as a and b, the scalars being a and b, the Fourier transform is going to be the linear combination of the individual Fourier transforms with the same constants a and b. This property can be easily proved from the definition of Fourier transform here. Instead of x of t, we need to simply replace this x of t by a times x1 of t plus b times x2 of t, and we can see that this equation turns out to be a linear combination of individual Fourier transforms. Next property that we're going to see is the property of time shift. The time shift property says that if we have a signal x of t whose Fourier transform is given by x of omega, then if we shift this signal by some amount, say t0 in the time domain, the corresponding Fourier transform is going to be e power minus j omega t0 times x of omega. That means if we shift a signal in time domain by certain units, say t0, then the Fourier transform is going to be scaled by the factor of e power j omega times this t0. This t0 is the amount of shift that x of t has gone through. Similarly, we can have the property of frequency shift. So let's have the another property of frequency shifting. That means shift in the frequency domain or the Fourier domain. This property says that, let's suppose if I have a signal x of t whose Fourier transform is given by x of omega, then let's suppose if we shift the signal in the Fourier domain by a certain amount, say x of omega minus omega naught. That means if we have shifted the Fourier transform itself by an amount of omega naught, then the corresponding change in the time domain would be x of t times e power j omega naught t. So this would be the inverse Fourier transform. What I mean to say here is that if I'm having a signal x of t whose Fourier transform is given by x of omega, then instead of shifting in time, if we shift in frequency by an amount, say omega naught, the shift is getting reflected in the time domain as the power of the exponential. You can note that there is no minus sign here, just because in the synthesis equation this exponential is positive. So we have this x of t being scaled by a factor of e power j omega naught t, where this omega naught is the amount of shift by which we are shifting this x of omega or the spectrum. Let's see another property. Next property, the fourth property that we are going to see is the property of time reversal. The time reversal property says that if you have a signal x of t whose Fourier transform is given by, say, x of omega, then if, let's suppose if we flip or make this time reversal in time domain, then the Fourier transform is also going to be flipped or reversed. This property is called as time reversal property of Fourier transform. That means that if we flip a signal in a time domain, the Fourier transform is also going to be flipped. Next property. Next property that we are going to see is the property of time scaling. These properties are similar to the properties of the Fourier series that we have seen in the previous lectures. So I'm not going to prove these properties because these properties, most of them have been already proved in the Fourier series when we have seen the Fourier series. So let's see the time scaling property. The time scaling property says that if I have a signal x of t whose Fourier transform is given by, say, x of omega, then let's suppose if we try to scale x of t by an amount, say a, where a is a scaling factor that can be either positive or negative but not 0. That means here a, of course it's not 0, then the Fourier transform is going to be 1 upon a mod a, to be very specific, x of omega by a. What this means is that, let's suppose if we scale the input signal in time domain by a factor of a. The frequency domain is going to be scaled by the same factor a, in fact the inverse of a, and also there is going to be a scaling factor in the magnitude, that is 1 by a. In simple words, what does it mean is that if we stretch the signal in time domain, it is going to expand. It is going to get, if we compress a signal in the time domain, it is going to get expand in the frequency domain. If we expand the signal in the time domain, it is going to be compressed in the frequency domain. So it's going to be vice versa. You can see that this scaling factor a, it's getting inversed, it is getting inverted in the frequency domain. It comes in the denominator. So if we compress a signal in the time domain, it is going to be stretched in the frequency domain. Next property. Next property is the property of convolution. Convolution in time domain. It says that if you have two signals, say x1 of t and x2 of t, and let's suppose if we have this x1 of t whose Fourier transform is given by x1 of omega. Let's suppose if we have another signal x2 of t whose Fourier transform is given by x2 of omega. Let's suppose if we convolve the two signals in time domain, the resultant Fourier transform is going to be multiplication of the Fourier transforms of individual signals. That is going to be x1 of omega times x2 of omega. This property is called as property of convolution in time domain. As we have the property of convolution in time domain, we do have a similar property in the frequency domain as well. So let's look at another property that is called as, you can see that before introducing the next property, in the previous property we have seen that if we convolve two signals in time domain, we are going to get a multiplication in the frequency domain. So if we convolve in the frequency domain, we should get a multiplication in the time domain. So vice versa is expected. So let's look at the property of multiplication in time domain. This property says that if I have these two signals x1 of t and x2 of t whose Fourier transforms are given by x1 of omega and x2 of omega, then, so let me write that once again. So if you have x1 of t whose Fourier transform is given by x1 of omega, let's suppose if I have another signal x2 of t whose Fourier transform is going to be x2 of omega. Let's suppose if we multiply the two signals in time domain, so that is x1 of t times x2 of t, then we should expect the similar kind of convolution. So the Fourier transform is going to be convolution in the frequency domain, that is x1 of omega convolved with x2 of omega. The only change here is going to be the scaling factor. The scaling factor is going to be 1 upon 2 pi. This is because of the 2 pi in this synthesis equation. You can see this 2 pi here. So there's going to be a factor of 2 pi. So you can see from this property that if we multiply in the time domain, we are going to get the convolution in the frequency domain, and vice versa. Let us look at another property. Next property is the property of differentiation. Differentiation in time domain. So this differentiation property says that if I have a signal x of t whose Fourier transform is given by x of omega, then the Fourier transform of the derivative of x of t is going to be j times omega times x of omega. This can be easily proved from again the definition of Fourier transform. By differentiating both the sides of the synthesis equation, we can directly obtain this property. Next property is the integration in time domain. This property says that if I have a signal x of t whose Fourier transform is given by x of omega, then the Fourier transform of integration from minus infinite to t x of t dt is going to be 1 upon j omega x of omega plus, this is important, this is going to be plus pi times x of 0 del omega, where this del omega is the delta function or the unit impulse function in the frequency domain. You can see that the differentiation property is completely the inverse of the integration property. The change is the second factor here, that is pi times x of 0 times del of omega. Otherwise this differentiation and integration is simply the inverse of each other, except this additional factor, that is pi x of 0 times del of omega. Next property. Next property that we are going to see is the Parsevals theorem. As we have seen the Parsevals theorem for the periodic signals, we do have a Parsevals theorem for the aperiodic signals as well. The Parsevals theorem states that the energy of the signal in time domain, that is integration of x of t mod of x of t whole square dt from minus infinite to infinite, is going to be equals to 1 upon 2 pi integration from minus infinite to infinite x of omega square d omega. What this property says that the energy of the signal in the time domain, if we calculate the energy of a signal in time domain, that is going to be equals to the energy in the frequency domain, just scaled by a factor of 2 pi here. These were the properties of continuous time Fourier transform, and you can see that most of these properties are akin to the properties of the Fourier series. We'll see more on this in the next module. See you then.